Okay, we're good? Okay, yeah, so it has come to my attention that I made another egregious error at some point back when we were talking about the absolute order. I think I said that all the maximal elements are Coxeter elements. This is not true. So the Coxeter elements are maximal elements, but you can have maximal elements that are not Coxeter elements. And I think if you do p set 4 and you look at the absolute order on the dihedral group I2 of 5, then you will find that there are some maximal elements that are not actually Coxeter elements. Anyway, that's sort of not related to what we're talking about here, but I wanted to correct that. Okay, so last time we were doing enumerative stuff, and I defined the q analog of the number k to be just this polynomial 1 plus q squared plus dot 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 plus q to the k minus 1, which if you set q equals 1 just gives you k. And yeah, so we're going to do stuff with this. So I guess I said there's sort of like this algorithmic procedure that you could use to compute this generating function w of q, which is the length generating function for the Coxeter group w. And then we noticed that like the answer we were getting was kind of nice, and there's an explanation for this. So here's the theorem, which I won't prove, but I guess I'll say something about it. Okay, so let me do this here. Theorem. So again, let's suppose that Ws is finite and irreducible. And let's let n be the number of simple reflections. Then there exist positive integers E1 through En. Okay, so E's are kind of overused in algebraic combinatorics. Like here, I've been using them for, well, I mean, we have E as like the identity element, and then we have the EIs, which are like standard basis vectors in Rn. That's not what this is. These are just some other integers, some other positive integers. And they are such that this generating function w of q can be written as the product from I equals 1 to n of the q analog of the number ei plus 1. Okay? And in particular, if you set q equals 1, then this is saying that the size of the group W is just the product from I equals 1 to n of the number ei plus 1. And if you want to look at the number of reflections in the group, so the size of T, this is the length of W naught. And we can write this as the sum of these exponents. And so this is because, remember, if you look at what this generating function is, it's like the sum over all elements of the group of q to the power of the length of that element. So if you look at the largest degree term, then there's just a unique element with the maximum possible length, which is the long element. So the leading term in this, or the biggest degree term in this generating function is just q to the power of the length of w naught. And so that is what you would get here if you just kept track of the the biggest degree terms in each one of these factors. Right? You'd just be adding up q to the e1 plus q to the e2, or sorry, it would be q to the e1 times q to the e2 times dot dot dot, and so that's just q to the power of this sum. Okay. Okay, so I'm not going to prove this, but I'll say that there are various proofs that people have found. So one is just a sort of type by type proof. So the idea is like, well, we have a classification of finite irreducible Coxeter groups, and if you think about the symmetric group, there's sort of like an easy way to do this. Actually, maybe I should write down what this is in the case of the symmetric group. So I think if you remember from like problem set 1, I asked you to prove that if, let's say W is the symmetric group Sn, or maybe I'll do Sn plus 1, so that I'm keeping, because in I want to be the number of simple reflections, so the number of simple reflections of Sn plus 1 is in. This is the same as An. Then we said that W of Q was the product from I equals 1 to n of just bracket I plus 1 sub Q. So this is like a p-set problem. And so this is saying that in the case of the symmetric group An, these exponents are just the numbers 1, 2, 3, 4. Like EI is just I. And so there's sort of like a kind of not so difficult combinatorial way of doing this. You just sort of think about inversions of permutations, and you can prove it like inductively. And then the point is you could do something similar for type B, because there's a combinatorial model of type B in terms of like signed permutations. You could do something similar for type D. And then there are also these exceptional groups like E6 and E7 and E8, and you could like check those by a computer if you wanted. So that's like one way you could prove this. Just go to each individual type and just do it sort of combinatorially or by computer. Or I guess you could check it by hand if you want, if you're patient, for some of them at least. There is a different, like a uniform proof that uses something called invariant theory, but I don't want to talk about invariant theory here, so I'm not going to give that. So anyway, this is just something that can be proven in various ways, but we're not going to prove it. Oh, but I should say what these numbers are, or what they're called. So the EIs are called the exponents of the group. So the numbers E1 through En are called the exponents of W. Oh, yes.
So in general, can you write as an infinite prop or no?
Right, so in general, I don't know if there's anything this nice. There is something similar in affine type. I actually don't remember exactly what it is, but I think it is written in the book, so I can check. I mean, I might as well say what happens. Oh, I guess I haven't actually defined affine type, though. Roughly speaking, so I've talked about like the affine symmetric group, which is sort of like an infinite analog of the symmetric group, because there's like this combinatorial model where you think of it as like infinite permutations with some conditions. There are also other affine Coxeter groups. There's like affine type B, affine type D. There's also affine type C, which is not the same as affine type B. And I guess the sort of moral of the affine Coxeter groups is that they're infinite, but they're kind of close to being finite in some sense. And there are nice things that you can do with the affine Coxeter groups. So let me see what they have written down about that. Let's see. So, oh, do they have it here? Yeah. Oh, okay. So yeah, I mean, I could even just write this down. So let WS be an affine Coxeter system. Let's say irreducible. So, okay, I haven't actually told you what this means. If you're interested, there's like a classification of these in the book, but the point is that like for each finite irreducible Coxeter group, or for many of them I should say, you can kind of extend it to this affine Coxeter group. In this, like, you can extend affine, or you can extend from like symmetric group to the affine symmetric group. You can go from like type B to the affine type B. So associated to this affine irreducible Coxeter group, there's a corresponding finite irreducible Coxeter group. We could let E1 through En be the exponents of the associated finite. Coxeter group. So for example, for affine type, so if you're looking at affine like S in tilde, the associated Coxeter group, the associated finite Coxeter group is just S in. And in this case, there's this formula for W of Q, which is, again, it's like a nice product from I equals 1 to N of the Q analog of EI plus 1, but divided by 1 minus Q to the EI. And so this makes it actually an infinite thing. Okay. So for example, if you wanted to know for affine Sn, like for Sn tilde, each EI would just be I, so you'd get, so like, okay, I could actually just write this down. If I take Sn tilde of Q, this should be the product from I equals 1 to N of bracket I minus, or sorry, bracket I plus 1 sub Q over 1 minus Q to the I. Okay? Yeah, so there are some similar nice things, but maybe not like in the full generality of like arbitrary Coxeter groups. Yes, Mitchell?
Is that the same thing as 1 minus Q to the N plus 1 over 1 minus Q to the power of N plus 1? Because that bracket is just 1 minus
Oh,
Q to the
yes.
N.
So yes, so bracket I plus 1 sub Q should be 1 minus Q to the I plus 1 over 1 minus Q. Wait, so what are you saying this should simplify how?
1 minus Q to the N plus 1.
Wait, to the N plus 1?
Or no product.
Oh, there's no product.
Yeah.
Oh,
Yeah.
okay.
And then divided by 1 minus Q. And then take that to the power of N plus 1. Or the denominator. This might be wrong.
So are you saying that maybe you get like a telescoping thing?
Yeah.
Yeah, because, so this would be like, you get a 1 minus Q, maybe it's to the N? Is it to the N?
No, but the very first term.
So you would get a 1 minus Q for each of these factors in the denominator. There are N of them. And then the I plus 1, so you get like, okay, so what is this? This is product of 1 minus Q to the I plus 1 over 1 minus Q to the I. But then we have a 1 minus Q. And the point is that like this telescopes. So for I equals 1, you get like 1 minus Q squared over 1 minus Q. And then you get 1 minus, oh, I see. The first term is giving you a 1 minus Q. Yes, right. And I think that's correct. I think that looks right. Yeah. Okay, yeah, so that's a good point. So in this case, it simplifies. Okay. Any other questions? Okay, so let me say some stuff about posets again. So let P be a finite poset. Then we can define what's called the Mobius function of P. This is going to be a map which, so I'll call it mu, or sometimes I'll call it just like mu sub p if I want to emphasize that it's for the poset P. And this is going to be a map from the set of ordered pairs x comma y, where these are both elements of P, but x is less than or equal to y in the poset. You could also think of this as like the set of intervals in the poset, if you think of identifying an interval with like the top and the bottom elements. So it'll go from this set to just, well, let's say Z. And it's defined by the following conditions. It's a recursive definition. Defined by the conditions first of all, mu of x comma x is always 1. And then secondly, so I'll say whenever x is strictly less than y, then I want the sum over all elements z in the interval between x and y. So recall that this bracket x comma y is the set of things that are greater than or equal to x and less than or equal to y. And I want the sum of mu of x z to be 0. Okay? So I'll show you an example of this. Let's do an example with this poset. So that's some poset. And okay, I'm supposed to assign a value to every ordered pair in this set, but that would get kind of messy if I did that for every possible interval in this poset. So all I'm going to do is look at the intervals that go from the bottom element up to some other element. So like I'll write down what is the Mobius value on like the interval from, or like this pair bottom comma like this element here, and I'll write the value next to the top element of the interval. So well, if we start at the bottom, so actually let me say I'm going to label an element x with mu of 0 hat comma x, where the bottom element is 0 hat. Okay, so this is 0 hat down here. Well, okay, so if I want to compute mu of 0 hat comma 0 hat, this condition tells me that should be 1. So I just get 1. If I want to do it for this element, then I have to use this condition. So I say this, like in this second condition here, this would be my x, this would be my y. So I'm looking at the interval here, which has these two elements. And I want the sum of the Mobius values on that interval to be 0. Well, I already know that this one is 1, so this one has to be -1. Okay. And then similarly, for the same reason, this one also has to go to -1. And then, okay, so what would this element go to? Or like if I want to label this element here, what would I label it with?
1.
Yes, 1. Because I want the interval from the bottom element to this element is these 4 elements. I want the sum to be 0, so I already have 1, minus 1, minus 1. So to make it 0, that has to be a 1. Then if I do this one, okay, what would this one be? 0, yes. And then this one should be 1 because I'm taking, so if I look at this one, the interval going up to there is 1, minus 1, minus 1, 0, so I need a 1. This one, I would look at 1 minus 1, so this should be 0. If I do this one, then I'm looking at 1 minus 1 minus 1, 1, so this is also going to be 0. And then for the top one, I just say, well, I have 1 minus 1 minus 1, 1, and 1. So those all sum up to 1, so this should be a minus 1 so that the sum becomes 0. Okay?
Are you assigning it to intervals?
Yeah, okay, so the point is like, the label that I'm assigning is mu of 0 hat comma that element.
Oh.
Yeah, which is sort of a common thing to do because like, if you want to think of like mu of x comma z, you could really think of it as like, I'm just going to focus my attention on the interval from x to z. Or sorry, if I want to look at the interval from x to y, like if I want to compute mu of x comma y, that actually only depends on the elements in the interval from x to y. So you could really just think of that as your poset, your interval. Like, okay, let's say I was looking with this poset and I wanted to compute what is mu of, or maybe here's a better way of saying it. Let's say this was part of a bigger poset. Let's say I had like some element over here and something like this, and okay.
Subtract it?
And well, so if there was some like bigger poset and I said I want to compute mu of this element comma this element, then this actually doesn't depend on any of the other stuff. Like the recursive definition here only involves stuff in this interval, so I could just ignore all of that other stuff and say, okay, I can just do this recursive description here and find that mu of this element comma this element is -1.
So, if I want to calculate the interval between x and y, and x is greater than y, then,
Or x is less than y?
oh sorry, like either way, like y is greater than or equal to x, then can I do mu of 0 comma y minus mu of 0 comma x?
Mu of 0 comma y minus, well, the issue is that, oh, well, I don't know, because like you might have other stuff, like your intervals might look like this. You might have like, here's 0 hat, and here's like x, and here's y, but like maybe there's also stuff over here. And like mu of 0 hat comma y, that's what you want. Like the issue is that that's going to involve these things over here as well, and not just the x. Is that what you're asking?
So if I do 0,
I mean, I guess another way you could write this is like, if I just rearrange this equation, I'm saying mu of x comma y is the negative of the sum over all z satisfying x less than or equal to z strictly less than y of mu of x z. That's just a different way of rewriting this. Does that make sense?
yeah.
Okay. Okay, well, you could wonder why I've defined this thing. So let me just mention a couple of examples. And these, so I just posted right before class the final P set. And one of the problems asks you to prove the following. So this is an exercise. If P is the nth Boolean lattice, then mu of, well, the bottom element of the Boolean lattice is the empty set, because I'm thinking of the Boolean lattice as like subsets of an n-element set under containment. So the bottom element 0 hat is really the empty set. And then if I go up to some element, which is some set x, this ends up being -1 to the power of the cardinality of x. This is one part of the exercise. And the other part is if P is the lattice of divisors. Well, okay, so I'll write it as the lattice of divisors of some positive integer capital N. You can really do this without choosing like some capital N and just say take all of the positive integers ordered by divisibility. You can define the same thing. I guess here I said let P be a finite poset, but it doesn't actually have to be finite. Like you can do the same recursive description. But anyway, just to make it finite, let's assume it's this. It doesn't really make a difference. In this case, if you look at mu of the bottom element, which is the number 1, comma some element, some number k, this is going to be -1 to the m if k is a product of m distinct primes and it's 0 otherwise. So it's 0 if k has a repeated prime factor. And otherwise it's -1 to the number of primes. And so, I mean, you'll maybe recognize this as like the number theoretic Möbius function. So like from elementary number theory, this is a function that people care about. And it's because you can do this thing called Möbius inversion, where like if you have a sum over all of, if you have some like number theoretic function where you're summing over all of the divisors of some number, then you can kind of invert this function in a way that I'll make precise in a second. So there's this notion of Möbius inversion for like in a number theoretic setting, which uses this Möbius function. There's also the principle of inclusion-exclusion, which can be formulated in terms of basically this Möbius function of the Boolean lattice. And more generally, there's a notion of Möbius inversion for any finite coset, which I'll state now. This is the Möbius inversion formula. So let P be a finite coset. And let's assume that it has a unique maximal element, or sorry, a unique minimal element. So with a unique minimal element zero hat. And let's say I have two functions, f and g. So f and g will both be functions that go from the poset P to, well, some field, I guess. I'll just say the complex numbers, but I guess it could be really like whatever. It could be a ring, I guess, or yeah, let's say a field. But anyway, let's take it to be the complex numbers. If these are such that this condition star, so g of y is the sum over all x less than or equal to y of f of x for all y in the poset. Okay, so I have these two functions, and they're related to each other by this formula saying that if you want to compute g, you just sum up the values of f over all the things that are greater than or equal to this input y. And so like in a number theoretic context, this would be like if you're summing over the divisors of some number. In the principle of inclusion-exclusion, this would be like if you're summing over all subsets of a set. So in this case, we can invert this formula and say, well, here we've represented g in terms of f, but we could represent f in terms of g. So then, let me call this double star. We can write f of y as the sum over all x less than or equal to y of g of x times the Mobius value mu of x y, where mu is the Mobius function of the poset p. And this is true for all y and p. Okay? Maybe I should say that, like, in the number theoretic context, people care a lot about the Mobius function, because it's real. I mean, you can relate the values of the Mobius function to things like the Riemann hypothesis, for example. So I guess that's important. And there are a lot of things that people really still don't understand about, like the asymptotic behavior of the values of the Mobius function. Like, it only takes values 0 and plus or minus 1, but you can ask for things like, as you go down the number line, how many times do you see a 1? How many times do you see a minus 1? And there's some very deep open problems about that. But anyway, here we're just talking about finite cosets. Where did my chalk go? Here it is. Okay, so here's the proof of this. Well, we're basically inverting a matrix. So I'm going to let M and M prime be the matrices with rows and columns indexed by P. And I'll define, so basically, like, for each element of P, there's like a row that's associated to that element. And similarly, there's a column associated to that element. And so I can say M sub yx, so this would be like the element of the matrix M in the row indexed by y and the column indexed by x, where x and y would be elements of my coset. So I want to define this to be 1 if x is less than or equal to y, and I'll define it to be 0 otherwise. And I should define also M prime. So M prime sub yx should be mu of xy if x is less than or equal to y, and it's 0 otherwise. So I guess you can think of, imagine we have a vector space where the basis is indexed by the elements of P, and these would be like matrices that are representing linear transformations from this vector space to itself. So we could also consider vectors, and these functions f and g that I've written down are basically vectors in this vector space. So let me write down what I mean by this. So think of f and g as vectors whose coordinates are indexed by P. Right, like, so I'm saying you have a vector where there's like, if you have x as an element of the poset, there's like an x coordinate of your space. And so the vector will have some number in that x coordinate, and that number, if I'm looking at the vector f, that would just be f of x. If I'm looking at g, it's just g of x. So then, if we think about it this way, what is star saying? Well, if you think about it, the condition star is basically a statement about multiplying a matrix by a vector. Right? So star is just this thing. This is basically saying that G is MF. So G, thought of as a vector, is the matrix M applied to the vector F. So if you sort of sit down and think about like what is matrix multiplication actually doing, and if you think about the definition of M, this is exactly this. Okay? And what is double star saying? Well, double star says that F is M prime times G. It's for the same reason. I'm just looking at this. This is basically multiplying the matrix M prime by the vector G and using the definition of M prime vector. So all we need to show, if we want this to imply this, well, we just need for M prime to be the inverse of the matrix M. So we just need to show that M prime is just M inverse. Well, this is not that hard to do. So we just say, well, what is the, if I take M times M prime, I'm just wanting to show that this is the identity matrix. So what is M times M prime? Well, let's look at the entry of this matrix M times M prime in the row indexed by X and the column indexed by Y. Well, if you just think about how to do matrix multiplication, this is the sum over all Z in P, because Z is indexing the coordinates, or sorry, P is indexing the coordinates, of M sub X Z times M prime sub Z Y. Okay? And this is just like the definition of matrix multiplication. But I can rewrite this as the sum over Z less than or equal to X of M prime sub ZY. And the point is that M sub XZ will be 0 unless Z is less than or equal to X, based on how it's defined here. And when it's non-zero, it's just giving me 1, so I'm just summing over all Z less than or equal to X of 1 times m prime sub zy. And well, what is m prime sub zy? Well, that's going to be 0 unless y is less than or equal to z. And if y is less than or equal to z, then I get this Mobius value. So this should be the sum over y less than or equal to z less than or equal to x of mu of yz. And just by the definition of the Mobius function, like the reason we defined it this way is basically to make this work. So this is going to be, well, 0 if x is not y, because we get 0 in that case. And if x equals y, we get 1. So this is 0 if x does not equal y, and 1 if x does equal y. But that's exactly saying that this is the identity matrix. We're just saying that the xy entry is 1 if x equals y, so you get 1s down the diagonal. And for the off-diagonal entries, you get 0. Okay, so this is the proof. Any questions about that? Okay, so I'm going to define something that I don't actually think I need to define, but it's a word that people use, so maybe it's good to at least see this terminology. Actually, I don't know if I'll need it. Maybe I will. We'll see. But this is the notion of an abstract simplicial complex, which is not really, okay, so an abstract simplicial complex. If you've never seen it before, it sounds scary, but it's not. All it is a collection of sets. Let's say a collection F of sets such that if I have some set A in this collection, so A is a set in this collection, then every subset of A is also in the collection. Okay. So it's just a collection of subsets that is closed undertaking subsets. Okay, so now let me go back a little bit to Coxeter groups. So let's suppose that W is an infinite Coxeter group. We'll define the nerve of W, or I guess it's called the nerve of WS. Either way. This is the set, so I'll call it script n of WS. This is the collection of all subsets J of the set of simple reflections, such that the parabolic subgroup generated by J is finite. And you can notice that the nerve is an abstract simplicial complex because, well, if the parabolic subgroup generated by J is finite, and then you take a subset of that set, then the parabolic subgroup generated by that even smaller subset should be finite because it generates a subgroup of a finite group. A subgroup of a finite group is finite. So I'll just note that n of WS is an abstract simplicial complex. So I want to think of the nerve together with the entire set S. Okay, so this is a collection of subsets which does not include all of S. Like S is not in the nerve because the parabolic subgroup generated by S is W, and W I'm assuming is infinite. But I'm just going to take the nerve and I'm also just going to add in this extra set S. And I want to think of this as a poset under inclusion. Actually, maybe we could do an example. I didn't write down an example, but we can probably write down one easily. Let's say I take, I don't know, let's say this is A, B, C. This is, well, maybe I want it to be a little bit interesting. Okay, let's say that's 4 and 8, and that'll be 3. So in this case, the nerve, so this is W, the nerve of WS is going to be, well, I should get the empty set, because if I take the parabolic subgroup generated by the empty set, that's just the identity element, which is finite, the trivial group. If I take just A, then I get the subgroup generated by A, which is just a group of order 2. So I'll just write it as A. Really I should be writing curly brace A, but let me just write it as A for simplicity. And then similarly, I should get just the singleton B and just the singleton C. If I take A and B together, that will be finite, because I'm just getting, well, that's like the dihedral group I2 of 4, which is finite. So I should be able to take A and B. I can also take A and C. Wait, maybe I should have made this example more interesting. Let's do this. Let's add an extra D. Okay. So D also is going to be in the nerve. So now, let's look at 2-element subsets. So A, B will be I2 of 4, that's finite, so I'll get A and B in my nerve. Similarly, B and C should be in the nerve because they generate I2 of 8, which is finite. A and C generate I2 of 3, which is just the symmetric group S3. And then now I want to look at 3-element subsets. So if I look at A, B, and C, they generate an infinite group, right? Because like the Coxeter graph of just if I look at A, B, and C, this is like not a finite Coxeter group. It's not on our list of the classification of finite irreducible Coxeter groups. So I don't have A, B, C. And let's see, A, B, D is in the nerve, because if I get rid of C, then I have like a disconnected Coxeter graph. So this would just be like the direct product of I2 of 4 and like Z2. So I would include A, B, D. If I take A, C, D, that is in the nerve because that's just going to be a copy of A3, or in other words, the symmetric group S4. So A, C, D will be in the nerve. And if I look at BCD, that is not going to be finite, so this is like a path with two edges where one of the edges is labeled by 8, and that is not on the list of finite irreducible Coxeter groups, so I don't include BCD. And then finally, ABCD is also not in the nerve. Okay. So if I was looking at this set, this post set, I would think of it as, well, I'd have empty set A, B, C, D, and then I'd want to include AB and BC and AC, which I guess is here. This is AC, and ABD, which would be here. Okay, so ABD is going to look like this. This is ABD. And then also ACD, which will be here. Okay, it's looking kind of messy, but hopefully that's okay. Sorry. I don't know, I could write it better. Yeah, why not? Okay, let's do this. Yeah, let's draw it a little bit spaced out. Yeah, I didn't plan the example in advance, so I'm just kind of doing it on the fly, but this is A, B, C, D.
I think you might have also forgotten to label one of your points. Like, I think there's an unlabeled one at the top that should be ACD.
Oh, yeah. ACD. Yeah, I'll get that when I copy it over. This is AB. This is AC. BC. It's like this. Then I want ACD here, which is going to have that and there. And then there's ABD, which I can put over here. ABD, which will be above AB, and it's above D. And then finally, so I'm taking this poset here, where I take the nerve together with just everything ABCD, which would be like this. Oh wait, I don't need this. Yeah. Okay. So this is my poset. So let's let mu sub n be the Mobius function of this poset. Of n of Ws union S. Right. Oh, I need this edge there. Yeah, now I think it's good. think maybe I wrote something wrong, but it's probably not
Why
important.
is CD not in the nerve?
Oh, why is CD not in the nerve? Maybe that's my issue. Oh, yes. There are a lot of two-element subsets that I ignored. Oops. Okay, good point. So I looked at, okay, I did AB, BC, AC, and I forgot all of the ones with D because I added this D in. Yeah, so AD should be in the nerve, BD should be in the nerve, and CD should also be in the nerve. Okay, thank you. Yes, that is what's wrong. AD, BD, CD should be added. And if I draw them here, okay, so AD, BD, CD, so ACD contains AD, and it contains CD, and ABD contains BD. Okay, this looks kind of awful, but whatever. And AD should contain A and D, and BD contains, yeah, I should have done this in advance, but whatever. B and D, and CD contains C and D. So yeah, that looks not good, but okay. You can imagine that there is a better way to draw this, and it's an exercise to do so. Okay. It's an exercise for Elliot at least. I mean, okay, it's literally like it's this, and it's under containment. It's like not that hard to, yeah, you should draw that, but yeah. Okay. Right, so maybe actually the thing that I wrote is correct. Yeah, this is correct. Okay, so if I and K are in the nerve, and K is a subset of I, then, well, if I look at the interval from K to I, this is just going to be isomorphic to a Boolean lattice. And well, basically the isomorphism is, maybe I should say it's isomorphic to the Boolean lattice of subsets of I minus K. And the isomorphism is that if you have some subset of I minus K, so let's say it's J, so let me write it this way. If J is a subset of I minus K, then I just map it to K union J. And that's going to be something that contains K, and it's contained in I. And this map is an isomorphism between the Boolean lattice of subsets of I minus K and this interval between K and I in this poset. And like we're using the fact that this is that the nerve is an abstract simplicial complex to say that like every subset, or like every set that is contained in I and contains K is actually in the nerve. Because, well, it would be a subset of I, and if I is in the nerve, then every subset of I is also in the nerve. And so what this means, hence, if we take the Möbius value, mu n of K comma I, well, this would just be what we would get, I guess maybe I Did I erase what I had for the, yeah, maybe I erased the exercise, but the exercise that's on the P set is to say that when you have a Boolean lattice, the value of the Mobius function is basically just -1 to the size of the set. So this is just going to be -1 to the size of I minus k. Okay. Okay, so here's a proposition, which is why I'm doing all of this.
Colin.
Yes.
This is really small, but that should have ABCD.
Wait, what?
Like NSW should have WS should have ABCD.
Well, the nerve doesn't have A, so yeah, so this is just the nerve, but then I'm unioning with the entire set ABCD for this post set. So I guess,
Oh, okay.
yeah, like when I wrote this, like nerve is this stuff, and then I'm sort of adding in the top element here.
Okay.
Yeah. But like I could also write this union S, and then I could add ABCD.
Yeah.
Okay, so here's a proposition. So if WS is an infinite Coxeter system, then, again, we're going to look at this generating function W of Q, except I'll write it as 1 over W of Q. This is going to be the negative of the sum over all subsets of the nerve of the Mobius value, mu in of, so now actually I'm taking mu in of Ks. So like in this post set that I drew, if I take my subset, like if it was AC, for example, I would be taking the interval from AC up to the top element here. So I have this Mobius value divided by WK of Q. This is for the, like it's the generating function that you get for the parabolic subgroup generated by K. So I think I can prove this, and then I don't know if I'll have time for an example, but maybe, if not, I'll just do it next time. But okay, so here's the proof. So let's just let n be the nerve. Instead of writing n of WS, I'll just write it as n. So if I is a subset of S, and I is not in the nerve, then, well, what does it mean to not be in the nerve? It means that if you take the parabolic subgroup generated by I, this is infinite. So I had this corollary that I wrote down over here last time, and it said that if you take this, if you have an infinite group and you write down this sum over K, a subset of I, K a subset of I, of -1 to the size of K divided by WK of Q, this was 0. This was the corollary where I said you write down this sum, and if the group is finite, this ends up being like Q to the length of W naught, and if the group is infinite, this gives you just 0. So we have this. So then, let's write down the sum over I not in the nerve of the sum over K contained in I of, well, the same thing, -1 to the size of K over WK of Q. This should still be 0. I'm just summing up a bunch of zeros, so I get 0. So hence, if I take sum over k, a subset of S, of 1 over wk of q, then I want to take, okay, so I'm just writing down stuff, but hopefully it'll make sense in a second. Sum over I containing k, and I not in the nerve, of -1 to the size of I minus k. This should be 0. Okay, why is that? Well, that's just rearranging this sum. I'm saying instead of summing over all I that are not in the nerve and then summing over subsets of I, I'll just sum over subsets of S, and then sum over, like, so k is just summing over subsets of S, and then I'm summing over I containing k and I not in the nerve. I'm just rearranging that sum there, pulling out the 1 over w of k, and I guess I've replaced size of k with size of I minus k, but that's not really going to change anything, I think, because I should just be oh, sorry. I know what I should do. I want this to be I minus k. And the point is, I can get this to be I minus k because if I fix I, well, why don't I just do it here? I think this is easier. I'm just changing the parity of this. I'm basically, like, if I replace the size of k by size of I minus k, that's going to either keep this sum the same or it's going to multiply it by -1. And well, the sum was 0, so if I multiply it by -1, it's still going to be 0. Okay, now this goes here. Okay, but if I look at the sum here, sorry, sum over I containing k and I not in the nerve of -1 to the size of I minus k, this is the negative of the sum over I containing k and I in the nerve of -1 to the size of I minus k. So why is that? Well, the point is if I just add, like if I move this over here and I just take the sum, like this sum plus that sum, then I'm just summing over all I containing k. I guess I should be fixing k. So this is for fixed k. I'm looking at this, but basically then I'm just summing over a Boolean lattice of like -1 to the size of I minus k. Essentially I'm getting like, I'm sort of doing this thing where I'm using an isomorphism between like a Boolean lattice of subsets of I minus k, saying that's isomorphic to this interval between, or wait, sorry. No, okay. What I'm doing, I'm basically just, yeah, I'm summing -1 to the power of some subset over a Boolean lattice. The point is I'm basically writing down some sum, which is supposed to be 0 because of the Mobius inversion, or sorry, because of the definition of the Mobius function, or in other words, this is just principle of inclusion-exclusion. So, okay. The summary here is that, like, if I move this over to this side, and I take this sum plus this sum, then the principle of inclusion-exclusion tells me that that should be 0. So that means that this sum is the negative of this sum. Okay, so hopefully that made some sense. But what is this? This is the negative of the sum over I containing k, I in the nerve, of the Möbius value of k comma I. That's just because of this. And if you think about the definition of the Möbius function, which I've erased, this is mu n of k comma s. And the reason for that is that if I move this sum over here, then I'm summing over all things in the poset that are greater than or equal to k. So I'm summing over the interval from k to s in that poset that I've drawn of the Möbius value, and that should be 0 because k is not s. Right, so okay, maybe I'll write down exactly what I'm doing here and then I'll finish. So the point of this is just if I were to write down sum over I containing k, I in the nerve of mu n of ki plus mu n of ks, this is the same as if I took the sum over I containing k and I in the nerve union s of mu n of ki. Right, so I'm just sort of adding this into the sum. But this is 0 because of the definition of the Möbius function telling me that if I sum the values over this, this is basically the interval in that poset between k and the top element. I'm summing the Möbius values, so I should get 0. So that's why this is true. And from this, okay, so finally, if you just plug this back in, you say, okay, this thing equals this Möbius value. So I get this is that Möbius value. So we have the sum over k, the subset of s, of 1 over wk of q times the Möbius value, which is what we wanted. Oh, but I guess I've also pulled out like this term here. Okay, maybe I won't go into the details, but I'll just say like the result basically follows from this by just taking this, plugging it in here, and pulling out the term corresponding to k equals s, and then just rewriting it, and you get this. Okay. So I guess that's the end of time. So I'll come back to this and do an example of this next class, and then after that, I think I will talk about Tableau, which is something that should be discussed in a algebraic combinatorics class. So, okay.